Hello everyone, how's it going? My name is Dan the Tutor, on a mission to become the world's greatest tutor. In today's video, we're going to be talking about how to find the electric field for an infinite line of charge. In my last video, I talked about how to do it for a finite line of charge. This is going to be an infinitely long wire, which is actually going to be easier for some reason, and you'll see why. So first, let's draw the setup. I have an infinitely long wire that goes forever up and forever down as far as we're concerned. And we want to find the electric field at some point P. Let's say it's a distance A away from the line of charge. This line of charge has infinite length, which means it has infinite charge actually. Yes, the charge of this line is infinity, which is why we say it has a linear charge density lambda. The equation for lambda, by the way, is Q over L. In other words, the charge Q, which is infinite, divided by a length L, which is also infinite, and we learn in Calc 1 that infinity over infinity is called indeterminate, which means it can be any number. And when I say any number, I mean lambda can be 2, lambda can be -4, lambda can be 3.6 times 10 to the -10th. It does not matter. Lambda can be anything, which is why I'm using variable lambda. And we're going to keep everything in terms of variables for this problem. And that's all I'm going to give you. So how are we going to find the electric field at point P? That is the question. So here's what we're going to do. When we have an infinite line of charge like this, we are not going to do that silly equation E equals the integral of K dq over r squared r hat. Yes, it does work, but this is ridiculous. We're not going to do that. Instead, we're just going to use Gauss's law. We can use Gauss's law because this line is infinitely long. If this had a finite length, in other words, if the problem looked like this, and the line had a length L, you cannot use Gauss's law, and this problem is just terrible. But again, I cover it in a different video. Okay, great. We're going to use Gauss's law. But what is Gauss's law? What's the equation, and how do I use it? The equation for Gauss's law is electric flux, which is electric field dot product with the area, is equal to the charge enclosed over epsilon naught. Or if you prefer and you don't like the dot product, because who does, you can say EA cosine theta equals charge enclosed over epsilon naught. Doesn't matter which one you do, but E is the electric field, what we're solving for. A is the surface area of my imaginary Gaussian surface, which I'll explain in a minute. Cosine theta just means I want one component as opposed to, x and y components. I just want one of the component. Sometimes it's x, sometimes it's y. In this case, it will be x, and I'll explain why in a minute. Q enclosed is the charge inside of my imaginary Gaussian surface, which again, I'll explain the Gaussian surface in a minute. And epsilon naught is just a constant, 8.85 times 10 to the -12th, which I will not be using for this problem. I'm just going to leave it in terms of epsilon naught because I have all variables. So that's the equation. I would memorize that if you haven't already. The left side of this equation is all about the Gaussian surface, which I guess now I have to explain what a Gaussian surface is. So let's draw that infinite line again. Here's the point I'm looking at. And my Gaussian surface is an imaginary surface. I can draw whatever I want, but it has to be three-dimensional. So for instance, I can draw a sphere around this infinite line of charge. It's not an infinitely big sphere, by the way. In other words, this line goes outside of it for sure. But it does have some radius, you can call it r or whatever. But it is a sphere. It is in 3 dimensions. Just want you to picture that. Now the problem with choosing this as the Gaussian surface, and I'm not going to choose a sphere. You should not choose any shape under the sun. Only one, sometimes 2 shapes are going to make sense. And I'll tell you which shape we're going to choose in a second. But the reason why you don't want to choose any surface you want is because if you think of electric field always points which way? Away from positive and towards negative. I don't care if this line is positive or negative. in other words, the black line, the line of charge. I don't care if it's positive or negative. Let's just say it's positive for convenience sake. The electric field lines would all point like this, straight out to the right, also straight out to the left. So those are my electric field lines because those all point away from the positive charge, and they're all going to be straight out like this. The problem with the sphere, then, is when I do EA cosine theta, I have a lot of angles going on here. Like there's a theta right there, there's a theta over here, and remember there's infinitely many of these blue lines, so there's going to be literally infinitely many angles I have to worry about. Not very fun. You can do it using an integral and polar coordinates, but I'm not doing that. So instead of doing all that nonsense, we're just not going to choose a sphere. The only two shapes that make sense for this problem are the rectangular prism, which I sometimes see, but pretty rarely, or the cylinder. And the cylinder is going to look like this. It's going to look like a big tuna can. Point P is going to lie exactly on my cylinder. It has to. And again, this cylinder is not infinitely long. I get to choose the dimensions. I'll choose length L, and normally I would choose radius R here for the cylinder. But earlier we said that that distance was A, so A is my radius. So the idea with choosing a Gaussian surface, why this is the correct one to choose, again, if I picture my electric field lines, now they're going to go straight through my Gaussian surface, and there's no more angle. Or maybe the angle's 90 degrees, but either way, I'm not going to have to worry about that cosine theta, because the angle is 0. It is not 90 degrees, and I can explain why, or you can just take my word for it. The quick explanation is that the way you measure an area, in other words, the red dotted lines, you always measure perpendicular to the surface, so the direction of the area is perpendicular to the lines themselves. The blue lines are also perpendicular. Because they're both perpendicular, they're actually parallel to each other, and that means cosine angle is 0. I know I said that really fast. It was probably confusing, and that's why you should just take my word for it. This is the right Gaussian surface, this cylinder. You can draw the cylinder every time. No, you do not have to draw the electric field lines, so I'll erase them. And no, the shape is not always this cylinder. It depends on the shape. I'm saying choose this example when you have the infinite line of charge. Okay. So the left side's all about the Gaussian surface. E is the electric field at the Gaussian surface. In this case, I'm looking at point P, which is on the Gaussian surface. So that's going to find us that electric field right there. We're solving for it. Great. A is the surface area of my cylinder, which, if you don't know, that's going to be 2 pi RL. By the way, 2 pi RL, or 2 pi AL, is the sides of the cylinder. It is not the top or bottom of the cylinder, which would be pi r squared for both, but I do not include those because the electric field does not go through the green top and bottom. It only goes through the side. And to prove that, let me draw the electric field lines again. See how my electric field lines go straight through the sides of the cylinder, not the top or the bottom. We don't have any field lines going like this. We just don't. And so for that reason, this is looking really good. So E times area equals charge enclosed over epsilon naught. Since epsilon naught is a constant, that means all I need to do is find charge enclosed, Q enclosed, and we're basically done the problem. What does charge enclosed mean? It's literally the charge from the line inside of my cylinder. Remember what I said a minute ago, the charge in the line is infinite. It's an infinite charge because it's infinitely long, but we're only looking at a section of this, the L section of this here. And so that means if you want to find it, we are going to be using that lambda equation that I mentioned earlier. Linear charge density lambda equals charge over length, in this case L. If we're solving for Q, which I am, just multiply both sides by L, and that's going to be my charge enclosed lambda L. So I'll just plug that in right there. So E 2 pi AL equals lambda L over epsilon naught. The last thing we do is we just solve for electric field and we're done. You may even notice that the L's cancel, which is great because that was a variable I made up, so technically it never existed, and so that would always cancel out for this problem. Then I'm going to divide both sides by 2 pi a, and technically epsilon naught is also in the denominator. So in other words, my final answer will be lambda over epsilon naught 2 pi a. You can organize that denominator in any order you want, but that's my answer. And as you can see, it wasn't terrible. It just involves a lot of knowledge about this Gaussian surface and knowing which one to choose. So again, just choosing the cylinder, this cylinder here, for the infinite line of charge will work every time. There's only a few shapes you really need to worry about, but this is one of them, and I'm going to try and make videos on the other shapes that you need to worry about too. So thank you all for watching. Again, this is the answer down here. And if you want, you can even just memorize that, and then you don't have to worry about this whole proof that I did. You can just memorize this result, but if you don't like memorizing, then, go through the 10-step process I just did. So thank you all for watching. Hope you have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.